finite element method analysis using Hypermesh of a cylinder with an internal radius of 100 mm, an external radius of 150 mm, and subjected to an internal pressure of 10 megapascals. So it's always nice to have some results to compare to. So we have actually the analytical solution. We have the displacement. We have the circumferential stress, and we have the radial stress. So we also have the values of the displacement, radial stress, and the circumferential stress in the internal radial and in the external radial. And this is the website where I got the results from. So let's do it. So now we want to draw two vertical lines to cut the circles. Let's create the surface of the cylinder. Now let's cut the surface because we only want to simulate a quarter of the cylinder as it is symmetrical. Now the trim is done. We can delete the part that we do not desire. We can also delete the nodes. Great. Now let's mesh this part. Maybe we do not need a size this small, so let's use 1 instead of 0.1 millimeter. Great. Now we can hide the surface, and we have only mesh now. So once you have completed the mesh, it's time to define the material. As you will notice, in this case, the material is irrelevant because in this case, as you can see from the formula shown at the start of the video, the stress, the circumferential and the radial stress and is independent of the material. So whatever material you use, it will yield the same result. The difference that a different material make is that the displacement is different. It's dependent on the properties of the material. In this case, we're going to use steel as the default material, and let's see if this is the material used in the example shown at the start of the video. So we're going to define these two properties enough for a linear analysis. Once we define the material, we have defined the property. Again, the thickness is irrelevant as we are doing a 2D plane strain problem. So a thickness of 1 will just do good. Once you have defined the material and the property, you have to define the boundary conditions. So let's do it. So in this case, we have two physics where the symmetry boundary condition should be applied. So let's do it. Now, on this side, we define a similar condition. Okay, now it's time to define the pressure. Here we need to do some maths. We're going to count the number of nodes in the internal radio. So once we get the number of nodes, we can now divide the total force by the number of nodes. That will yield the individual forces that should be applied in the nodes. However, what we have is a pressure, so we need to transform the pressure into force by multiplying the pressure times area. In this case, a quarter of the total area. So the total force would be the pressure, which is 10 megapascal, multiplied by 1/4 of the length of this arc length, this which is pi times in the internal radial divided by 4, which is 785. And 785 divided by the number of nodes, which is 158, gives us a force per node of value of 4.97. So let's assign that force to the nodes. So for the definition of the forces which are perpendicular to the inner radius, we should create a cylindrical system so that we can apply the force which are normal to the inner surface of the cylinder. So for the creation of the system, let's define its origin. And in this case, it should be the 0, 0 node. So now we are going to create our cylindrical system. We go to systems and we pick the origin as this node. The x-axis, which is the rho or radial axis, we pick this point. And for the theta axis, which is perpendicular to this curve, we can pick actually this node here. Oh, so yes, now the cylindrical system is created. We can go to forces and apply our force. As we said, the magnitude of the force is 4.997. Sorry for that. And the nodes are those nodes on the edge of the cylinder, which is the internal edge. So let's select them. And the axis system is the local system, which is this one. And we should pick the x-axis, which is the radial axis. So as you can see, the forces are applied perpendicular to the curve. Okay, now the forces are completed. Now we should go and create the arrow step. Let's call it. Let's select a linear static analysis type, and for SPC we choose the SPC component, and for the load we choose the pressure component. Alright. Okay. Now make sure that you guys assign the property to the mesh. So let's do it, and make sure that you guys assign the material to the property. So let's do it. And now we can run the simulation. Let's check the results. First, we're going to check the stresses. So as you can see, in the radial direction, we have a value of 5 in the inner radius. So somehow this is the half of the stresses that we should be getting. So I realized that for the formula for the forces, we actually applied a half of the value of the forces because I calculated the perimeter as the pi times internal radius, which is not right. It should be pi times the internal diameter. So let's update the value of the forces. So for that, we should go to forces and update, and we choose the rods that contained in the collector pressure, and we changed its value. So instead of 4.97, it should be this value. and then we click on update magnitude. Great. Now we can run the simulation again. So we can check the stresses again. The values of the stresses on this element are of 9.75, and the value on the outside is almost 0. So this is the radial stress. For the circumferential stress, let's check again. So the value of the stress in the inner radius is 26, and in the outer radius is 1.6. As you can see, you may have noticed that there are some elements with strange color at the bottom and or at the top of the cylinder. Those are called singularities. We should not take into account those points. And so you can see that the results match perfectly with the analytical solutions. So we can see that we have simulated this case successfully. So thank you guys for watching. Any doubts or any comments, please leave them below. Bye.